magnetic field due to an infinite conductor. So when we talk about infinite conductor, it doesn't necessarily means that conductor is infinite. It means that it is actually a very long conductor. So let's suppose this conductor is actually moving here towards point X towards point Y, and a current that it conducts or it carrying is current I. So we have to find the amount of magnetic field that it is producing. So as we know from Ampere's law, now suppose at a point P we will find what is the current that it produces. So we will actually assume an Amperian loop that we have learned according to Ampere's law. At a particular point, through this particular point we will assume an Amperian loop, and we know that all the points in this loop will have a certain magnetic field D. And let's suppose this loop has radius R, and the line element, it's at the direction of the tangent, and also in the same parallel direction is the magnetic field D. So using Ampere's law or Ampere's circuital law, we can write circular integral B dot dl is equal to mu naught I. So this is given by Ampere's law. It says that when we have this two line element and the magnetic field, and we have this Amperian loop, so the magnetic field would be, the line integral of this magnetic field would be equal to mu naught I. So let's just break this a little more. Since this line integral, it's a dot product, so I can write it as B dl cos theta. Theta is the angle between these two, and which is parallel, they are parallel to each other in the same direction. So theta is nothing but 0 degree. So cos 0 degree is nothing but 1. So I can also write it as, so this is mu naught I. So this is B dl equal to mu naught I. The total magnetic field is nothing but B. So the total magnetic field is B. The total length, that is the circular integral of dl, I just take B out, and circular integral of dl is equal to mu naught I. It means that now this is not the vector, this is the length element, this is the length, and the total length means the addition of the total length for the circular loop would be nothing but 2 pi r. Right, as we know, this is 2 pi r. So B into 2 pi r is mu naught I. From here we can easily calculate B is nothing but mu naught I by 2 pi r. Right. So using Ampere's law, so this is Ampere's law, using Ampere's law and applying to this particular case at a particular point P, and imagining an Ampere loop, we can find the magnetic field given by B equal to mu naught I by 2 pi r. Just to have little more symmetry, we can also write it as mu naught by 4 pi into 2I by r. Just because most of the expression has mu naught by 4 pi, so mu naught by 4 pi into 2I by r. So this is a magnetic field that is produced by a very long current carrying conductor. Now what things that we can just infer from this particular derivation? Now you see, throughout this Amperian loop or throughout this loop, magnetic field is constant. So you take any point on this particular loop, magnetic field is always constant. Therefore, if I take all the points where magnetic field is constant, suppose I take a particular case, if I take all these points, then it will form a concentric circle in which all the magnetic field is constant. So these concentric circles where the magnetic fields are constant, they are also called as magnetic lines, because in these lines the magnetic field is constant. And also if you see throughout, as it is a current which is moving around, therefore you will see that this particular arrangement has a cylindrical symmetry. In the sense, when you imagine this as a cylinder, all the points in a cylinder, suppose if you take a particular radius, either you take here or you take here. So even if you take another circle of the same radius here, this also would have the same magnetic field. You take another point here at the same radius, this also will have the same kind of magnetic field. So they all move together like a cylinder, and therefore we can tell that they have a cylindrical symmetry. This is the first point to be noted, that we have concentric magnetic lines and they have a cylindrical symmetry in this case. Also, one more thing, from this relation you will be able to see that B is proportional to 1 by R. It means that as you move from this current carrying wire, as you move away from the wire, the magnetic field actually drops down. So from the wire, as you go further in the radius, the magnetic field moves down. And also there is another thing that we can see, that if I have the current direction as this, then when you imagine an Amperian loop at this point, at the point P, the tangent through this would be your direction of magnetic field, which is again a proof, or it is a kind of theory that if the current is moving, then your magnetic field direction would be towards this direction. This also gives a proof for the experiment, or this gives a theory, basis of theory for the Oersted experiment. As you remember that in Oersted experiments it was told that suppose if I keep a magnetic needle, the north direction always move towards this direction if the current carrying wire is moving. So this Ampere's theory, and specifically this theory, also gives the theoretical support to Oersted experiment. And this is also the similar thing we see in Ampere's swimming rule, the similar thing we see in right hand rule. So this also gives us a very strong basis for the direction of current and the magnetic field due to the current. Not only that, it tells how the magnetic field direction, it gives magnetic field how it is related to the radius, that it gives also it gives the concept of magnetic field line. So there are so many things that we can infer from this one particular derivation.
If you like the video, then press the like button, subscribe to the channel and press the bell icon.